So let me, in order to make this maximally useful, let me, well, I'll tell you first what the object of study is. So we're interested in the following physical question of we might imagine we have some time-dependent background, some FRW cosmology, where the metric looks like negative dt squared plus a squared of t dx squared, for example, which I can also write as some a squared of eta, as you usually pull out a conformal time, so negative d eta squared plus dx squared. Okay? So this is a very broad class of cosmologies. And we can imagine that we have a scalar field that lives in this space-time, but with a mass that's conformally coupled. Okay, what that means, to say the mass is conformally coupled, it means that by a conformal transformation, you can undo it and just bring it back to flat space. Okay? But we're going to imagine the interactions are not conformally coupled. So the mass is such that after you do a conformal transformation, you come back to flat space, but now there will be time dependence in the interactions. Okay, so let me not go through all this conformal transformation, blah, blah, and just immediately go, I'll still call the variable eta, but what we're really talking about is a class of time-dependent actions with time-dependent coupling constants that look like a half d phi squared, so just normal free propagation, but the coupling constants can depend on eta. And in fact, we can imagine arbitrary polynomial interactions like this. So in fact, it's even more general than cosmology in that sense, because if you pick a particular A of eta, that gives you a very specific formula for these guys. It says that gi of eta is, roughly speaking, A of eta to the power of gk of eta is A of eta to the 4 minus k, I think. Anyway, some power like that, but we don't even need to assume that, okay? We're really solving a very general problem with time-dependent coupling constants, okay? And in fact, we could, even if we like, imagine it's not time-dependent, okay? And, but we're allowing the coupling constants to be time-dependent. But the question we're asking is about what the wave function of the system is, a function of phi, at a late time slice here as eta goes to 0. Okay? So we have eta goes to 0. And we want to know what is the wave function that now just depends on some coordinates x on the boundary, on the spatial boundary. Okay? Now, there's a standard path integral picture for this, which is that this wave function is what we get just by doing the path integral over bulk phi with the boundary condition that phi of x as eta goes to 0 asymptotes to this phi. Let me call this sort of capital phi of x. This is the Feynman path integral prescription for calculating the wave function. Okay, so the wave function of phi of x, the wave function of this capital phi that only depends on the spatial x is a path integral over all phi's that depend on time, e to the I action, with the boundary condition that phi in the bulk matches capital phi of x on the boundary. That's the Feynman path integral prescription for calculating a wave function. Okay? For calculating the vacuum wave function. Okay, so that's what we want to learn to calculate. So we can even do this in flat space. We can even start doing this in flat space. And let me actually, yeah. So that's the object that we want to learn to a compute. And let me just quickly sketch what the derivation of the Feynman rules is for this calculation. The first thing you want to do is take care of this. Okay? So what you do is you say that phi of x and eta is first just in the free theory. Let's forget everything else. Just imagine the theory is free. Okay? Then what do you want to do? You want to say that phi is equal to, well, this capital phi of x on the boundary. Okay? So that makes it match at eta equals 0. And then it's reasonable to expand around the solution of the classical equations of motion. Right? A solution of the classical equation of motion that has that as a boundary condition. Now, what are the solutions of the classical equations of motion? They are some a e to the I magnitude k. Now, so if we're okay, so we want to we're trying to make this happen, right? 5x. So let me immediately go to Fourier space to make my life easier. I have translational invariance. So it's the same thing in Fourier space. As eta goes to 0, I want this to go to this phi in Fourier space. Okay, and now it's easier. Now it's easier to write the solution. So there is something that is the classical solution that looks like phi of k, and then it's e to the I, the magnitude of k, that's the energy of k, eta, right? So that's something that at eta equals 0 matches and is just the usual oscillatory solution away from that, okay? Now, in fact, I can have a general solution with a plus b, and with just the requirement that a plus b equals 1, that would also guarantee that this matches. But here we're putting in some physics. And the physics is that if you want the vacuum wave function in the deep past, you want to keep solutions that oscillate as e to the plus ik eta as you go to eta equals minus infinity, and not e to the minus ik eta. The ones with e to the minus ik eta would blow up when you added the I epsilon. You want them to damp as you add the I epsilon. Okay? So the physics here is that we're trying to select with these boundary conditions that what's coming in from the past is the vacuum. Okay? And this is the usual logic behind the Feynman I epsilon. If we had longer, if I didn't have to leave at 4 a.m., we could talk about all these things in more detail. But anyway, there's a very simple reason. But all the modes have to go like e to the plus ik eta as you go off to eta equals minus infinity to the deep past. So that's what takes care of that. Okay? All right. So and plus some delta phi. So all I'm doing is I want to write phi as something which is guaranteed to match the right boundary conditions plus a perturbation. Okay? And already if I take this and I shove it into the action, because this thing is imaginary, if I shove this into the action, then I find so the action is like is in this momentum space. There's some d eta phi squared, and then there's a minus k squared phi squared. Okay, so that's the free piece. And then I have some things that go like some g phi cubed plus dot dot dot. Okay, but let's just even focus on the quadratic piece. If I take this solution and shove it in there, I can very easily do the time integrals. Actually, better than doing the time integral over eta is to just recognize this as a total derivative. Recognize this d eta of in the usual way. We can recognize this as d eta of phi d eta phi. Yeah, so what is this? So if I take phi and I shove in this, let's call this thing phi classical, okay? Then just this integral d eta phi classical squared minus k squared phi classical is up to a total is the integral d eta of this first piece is d eta of phi classical d eta phi classical, and then minus what's left is phi classical times d eta squared plus k squared phi classical. That piece is 0 because it satisfies the equations of motion. So this piece only gets a contribution from eta equals 0. So I'm just left with phi classical d eta phi classical at eta equals 0. And so what is that? This is phi k squared. And then the d eta pulls down an ik. So that's the action. And therefore, finally, e to the I action is just equal to e to the minus k times phi classical squared. And that's the ground state of the harmonic oscillator. Okay, so that's the standard way with the Feynman path integral that you see the ground state of the harmonic oscillator. Okay? All right. Yeah, okay, sure. Thanks. Yeah. Okay, so, but now let's put in the next correction. Okay? So if I put in the phi cubed term, then the first thing that I'm going to get, if I put in the phi cubed term, is that I'll get something that looks like the integral phi classical cubed of eta. Okay? So, I mean, let me do the expansion, right? I'm just expanding phi equals phi equals phi classical plus delta phi. And so we just saw that the action turns into the quadratic action, which only depends on phi classical. That we computed already. And now I have pieces that look like, for example, from the cubic interaction, I have a piece that looks like g phi classical cubed plus phi classical squared delta phi plus dot, 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 right? So let's first look at the first correction here that goes like g phi classical cubed, for example. So what is that guy? So that's also very easy. So from that, I get an integral minus infinity to 0. And let me just draw it graphically here. I have a phi classical cubed. So here's eta. I'm integrating over eta. So here's 3 factors of phi classical that I can just sort of write like that. And so what am I getting? I'm getting an integral eta. And from each one of them, I get a phi classical of k1, phi classical of k2, phi classical of k3. There's the delta function for momentum conservation, as usual. But then the interesting part, the eta-dependent part, is e to the I magnitude of k1 plus magnitude k2 plus magnitude k3. Okay, so from this part, we get something that looks like, let me write it, phi classical of k1 to phi classical of k3. And the integral minus infinity to 0 d eta e to the I k1 plus k2 plus k3 eta. And this gives me I over k1 plus k2 plus k3. So I'm not going to be careful about the i's and stuff here. Okay, but this integral gives me 1 over the sum of the k's. So let's see, already at this point we've computed what this wave function is to cubic order in phi classical. That's what we care about, the dependence on phi classical. And so the wave function is psi of phi, psi of this, psi of phi of x, this is phi of k. Okay, phi classical is the bulk thing. The phi of k was what I had on the boundary at eta equals 0. So psi at phi of k is e to the minus, I'm integrating over k here, so I'm not going to keep writing that, an integral over d cubed k or whatever. But I have a piece which is k phi k squared. That's the quadratic piece. And then there's a cubic piece, which is like there's a delta cubed k1 plus k2 plus k3, phi of k1 to phi of k3, 1 over e1 plus e2 plus e3. And here I assume that there's no time dependence in the coupling constants. Okay, so this is what I would just have if the g was just time independent. I just wanted to do like a simple example here. And then we get plus ... Okay? So now what I want you to see from here is that what we're interested in, the object of study, is this wave function. And we can calculate it with Feynman diagrams, so I'm not going to keep writing down the phis over and over again. We're interested in the part of the wave function that has n phis in it. And so we want to see what that part looks like in general. Let me do one last piece of this calculation. So nowhere so far have we had to do the path integral over delta phi yet. So to get that piece, in this expansion we had the integral phi classical d8. We had s quadratic that depended on phi classical, and then we had the integral of phi classical cubed, which we just did. And now we hit the first new piece, which is phi classical squared delta phi classical. Okay? So now we're going to do the path integral over delta phi classical. Okay? And so doing that path integral is going to give us, well, sort of Feynman diagrams. In this case, at leading order, here's 2 phi classicals going out. These are those 2 factors. Sorry, this is delta phi. And now we're going to have a propagator for delta phi. So that's what we're going to have. So here we're going to have a propagator for delta phi. And it's going to go from some time eta 1 here to another time eta 2. Okay? So now this is new. What we're going to get from this contribution is an integral. From here, we'll get e to the I k1 plus k2 eta 1 from these 2 factors. From these 2 factors, we'll have an e to the I k1 plus k2 eta 2. And here, we'll have a propagator. We'll have a propagator that depends on eta 1 and eta 2. Right? So these are just standard Feynman diagrams. Okay? But now we can nicely see what the rules are. So what are the rules in general? If you want some contribution to the, if you want any contribution, you just draw the same old Feynman diagrams you'd always draw. So we just drew some. So we just drew this 3.1, except now all the lines go to infinity. Okay? Now we drew that one. Now we can draw much more complicated ones. Okay? And so on. But what are the rules? The rules are that for every line going to the boundaries, there's a factor of e to the I k eta. Okay, for every line going from a vertex eta to the boundary. Each one of these propagators going to the boundary, from eta to the boundary, has a factor e to the I k eta. And for every propagator between an eta 1 to eta 2, we have to write some Green's function. G, that depends on the k of this internal line, k internal. It depends on eta 1, eta 2, and k internal. OK? And so this is just like familiar Feynman diagrams. The only unfamiliarity is that we're not used to usually working in we're used to working in momentum space for everybody. Here we're only working in momentum space for spatial momenta, and we're working in time for time. And that makes sense because we don't have time translational invariance. Okay? We're asking a fixed question at a fixed eta, and that's breaking time translational invariance. So now all I have to tell you is what that propagator is. And, well, you know that these propagators are supposed to satisfy the equation of motion with a source term, right? So it's supposed to satisfy d eta squared plus k squared g of eta and eta prime is equal to delta of eta minus eta prime. OK? And so there's a usual sort of time-ordered product type solution, right? Because the solutions have to look like, here's, as a function of eta, here's eta prime. So out here, it has to look like e to the, so out here at very early eta, remember we want everything to go like e to the I k eta, and not e to the minus I k eta. So at very small eta, at eta much earlier than eta prime, this has to look like e to the plus I k eta. Out here, it has to look like e to the minus I k eta. And by integrating this equation across eta equals eta prime, we get a jump on the first derivative. Okay? So that tells me what linear combination of those two I need to have. Okay? So one solution to this differential equation, the usual one we'd write down with Feynman's prescription, the time-ordered product prescription, would tell me that G is equal to 1 over magnitude of k times e to the I k eta when eta, sorry, e to the I k eta minus eta prime when eta is smaller than eta prime. So I put a step function of eta minus eta prime. Sorry. When eta prime is bigger than eta, plus the other way around, e to the I k eta prime minus eta when eta is bigger than eta prime. Okay, so that's the usual Feynman propagator. Okay, just in this slightly unfamiliar space, which is in time and working in spatial momenta. All right, so that's just what you get by, I mean, you get this 1 over k by matching the jump of the discontinuity across that in the usual way we're familiar with from in quantum mechanics. All right, that's a Feynman propagator, but it's not the propagator that we want, actually, because our delta phi has a specific boundary condition that it has to satisfy. Our delta phi has to vanish at eta equals 0. The whole point of introducing the split between phi classical and the delta phi is that we wanted to ensure the correct boundary condition of the path integral at delta phi equals 0. So our propagator must enforce that delta phi vanishes at the boundary where eta equals 0. And this one does not do that, right? As, let's say, as eta goes to 0, this term, if for eta prime fixed, I just get this term and not that term, and this thing is plainly not 0. Okay? All right. Sorry, I get this one, but not the other. Anyway, I just get one or the other, and it's not 0. Of course, this is only one solution to this differential equation. I'm free to add any homogeneous solution to it that I like. And so I have to add a homogeneous solution that makes this happen. And so let me actually just write it down here. well, let me write it down. The solution that we want in the end is that this g of eta prime and k is equal to 1 over k times e to the I k eta minus eta prime when eta prime is bigger than eta, plus the other way around, but there's a correction that's just a homogeneous solution. So it's e to the I k eta, e to the I k eta prime. These k's are just magnitude of the vector k. I should, whenever there's no confusion, I'll try to do that. So you see, this solution, just the product of 2 e to the I k eta, trivially just satisfies the homogeneous equations. But you see what it does. When either eta or eta prime gets close to 0, this piece kills the other one, and they get 0. All right? All right, so now we're done. So these are the Feynman rules now. Okay? The Feynman rules are that when the propagator goes to the boundary, it's just e to the I k eta. And when there's a propagator connecting 2 points, I get that funny expression with 3 terms. Okay? 2 terms is like the normal time-ordered product. And this one term that is enforcing, this one term is enforcing that we're calculating this wave function with these boundary conditions that delta phi equals 0. Okay, any questions about this? So this is a crash course on the calculating wave functions. Okay, and now you can put in time dependence if you want, because we're working in time space. So when you do the integral over the time, you have vertex factors at all those vertices, and they can be time dependent. Okay, so easy peasy. So these are the Feynman rules for calculating the wave function. Okay. If you've ever heard of the Schwinger-Keldysh formalism or the in formalism or things like that, you can forget it. Okay, you don't need to know it. This is just as good, right? And it's directly just calculating the wave function. Okay, any questions about this? All right. So this is just introducing you to the objects before we get to anything fancy. So in the context of cosmology, or in our toy model, these coupling constants are time dependent. But in the end, the object we're interested in is static, right? The object we're interested in just depends on spatial momenta and nothing else, right? So, and indeed, this is an even harder version of the question that I began the lectures with, right? And the harder version of the question is, what are the rules that tells you, I mean, for the S matrix, we don't know what are the rules that determines whether the S matrix comes from causal evolution. It's even harder here. I just give you a wave function. It depends on spatial momenta. There's nothing even that remotely looks like time. There isn't even any analog of unitarity to check. There's no in and out states, right? I just have this static thing. How, from the information in these spatial correlations at late times, how am I supposed to figure out if it came from consistent time evolution in the past, and so on and so forth, right? With just a wave function, there isn't much you can do. Maybe you can check if it's normalizable or not. But in perturbation theory, that's pretty trivial. If the sign of the Gaussian term is correct, it's normalizable in perturbation theory. So clearly there has to be much more to the structure of the wave function than just that. But what is it? Okay? And so the goal is to try to learn to calculate it in perturbation theory. And just like we see structures and scattering amplitudes that speak to us about what the structure might be that determines them, the goal is to try to see similar structures in the computation of these cosmological wave functions. Okay? But before getting too mystical, I want to point out something really important, that this wave function contains scattering amplitudes. So they in fact generalize scattering amplitudes. Okay? And they contain them and generalize them in a very beautiful and simple way. Yes?
Are we imposing anything on the space-time? Does it have to be conformally flat or anything like that?
No. In fact, I mean, yeah. Well, I mean, in the thing that I'm talking about, the only thing is that it has spatial translational invariance. Okay? So I went to spatial momentum space. But other than that, any kind of FRW cosmology is perfectly fine. The main simplifying assumption I made is that my scalar was conformally coupled, so that the kinetic term was time independent, and only the interactions are time dependent. Okay? So that's a simplifying assumption. But still, there's plenty of time-dependent stuff that we could be talking about here. Okay? But one thing I want to mention is that, so let's look at something simple. Say we had a phi to the 4 interaction. We did a phi cubed. The leading thing here to the wave function would give me, lambda, the coupling constant, and I'd get, from the time integrals, I'd get 1 over k1 plus k2 plus k3 plus k4, and then a delta function for momentum conservation, of course. Okay, so that's the kind of leading, interesting quartic piece of the wave function, right? Now, so here's our question. We have the static quantity. What are the consistency conditions on the static quantity, and so on? But that formula should strike you as a little bit familiar. I mean, before looking at any formulas even, again, what is the data that specifies the observable that we're talking about? The data is a bunch of momenta that add up to 0, right? A bunch of spatial momenta. So the data is like one of the polygons that we like drawing for scattering amplitudes. Okay? You give me a bunch of spatial momenta that add up to 0. That's the space on which these wave functions live, right? It's exactly the same as a space of scattering amplitudes that are also a bunch of momenta that add up to 0, spatial momenta that add up to 0 by momentum conservation. There's only one thing missing. We have something extra in scattering amplitudes. We have energy conservation. Okay? So a scattering amplitude for the same quantity, the same 4-point function as a scattering amplitude, would be lambda delta function for the sum of momenta, and then we'd have a delta function for the sum of the energies. Okay? Whereas here instead we have 1 over the sum of the quote-unquote energies. Okay? So now, and why is the difference? Where does this delta function come from normally for scattering amplitudes? It comes from an integral e to the I energy eta for all the particles. So energy 1 plus energy 4 eta. But these integrals run from minus infinity to plus infinity. So that's where we get the delta function. Whereas our new ones are going from minus infinity to 0. And that's where we get a 1 over the energies instead. Okay? So, but notice then that this quantity depends on exactly one extra variable compared to a scattering amplitude, the sum of all these energies. And therefore, for physical momenta, these are all positive numbers. But you can analytically continue. If you analytically continue to make 2 of them, let's say, positive and 2 of them negative, then you can hit this as a pole. What is the residue on that pole? It's the scattering amplitude. Okay?
So really,
So,
what you consider as half of scattering.
Yes, it's kind of a half of a scattering amplitude, exactly. And but there's a very good and simple general reason for this, and that is if you have an arbitrarily complicated graph, whatever the hell is going on, right? Whatever the heck is going on. If you take all the time integrals here, and you send all their etas to minus infinity together, okay? You send all these things to minus infinity together, then, sorry, first of all, where do any singularities possibly come from? The singularities come from the fact that these integrals are unbounded, okay? And as any eta goes to minus infinity, there's an e to the I energy eta that's damping everything out. But as if all these etas go to minus infinity together, there's an overall factor e to the I, the sum of all the energies, times that sort of center of mass eta for all of them. So if you tune the sum of the energies to add up to 0 by this analytic continuation, then that integral will be unsuppressed and we'll get a pole. But where is the pole coming from? It's coming from the region as eta goes to minus infinity. But you see, as this stuff gets further and further from the boundary, it can't tell whether the boundary is sitting there at eta equals 0. It's getting infinitely far from it. So the answer is the same as what we'd get for the scattering amplitude. Okay? So this is a very simple and deep thing, that these cosmological wave functions, amazingly, they contain the scattering amplitude. I think it's an incredible thing. It's a technically trivial thing, but it's a sort of physically very deep one. That there's a static question you ask about the universe today, but it contains in it all the dynamical physics of particle scattering processes by this appropriate analytic continuation. This is much more interesting than LSZ reduction. Okay? This is vastly more interesting because it says that on one spatial slice late in the future, this static observable contains in its appropriate continuations all of the dynamics of scattering amplitudes. So these objects generalize scattering amplitudes by a single variable, the sum of all the energies. Okay? And by the way, away from the sum equals 0, these things don't have infrared divergences. They're perfectly well defined, beautiful, nice generalizations of scattering amplitudes.
So
Yes?
it's my understanding of what you consider really is adiabatic scattering matrix.
Sorry?
This is adiabatic scattering matrix.
Not really, because it's not really scattering in the end at all. There's nothing that's scattering at all. Yeah, right.
Okay.
Yeah.
Adiabatic Müller matrix.
Oh, perhaps, yes.
Yeah.
It is definitely adiabatic. It is definitely adiabatic, yes, right.
Very well known that adiabatic Müller matrix really is related
To the scattering matrix. Yeah, fine, yes, right. So this is the object that we're talking about. Yes, this is very old. This is very, very old. Yeah, I didn't know what the names were for these things, but yes, that they're
about 50 years ago, I have written papers
Oh.
about this subject.
yeah. But now what I want. So here I'm just introducing the object, and also motivating is connected to scattering amplitudes. And given that there are so many geometric structures associated to scattering amplitudes, it's very hard to believe that they don't extend away from this surface where the sum of the energies is 0, right? It's very hard to believe that they disappear the second you go away from the sum of the k's equals 0. So it's very likely that there's some extension of these things that also makes sense for these cosmological questions. And that's what we want to talk about. All right. Maybe I can just stop there for a second. Are there any questions? Are the Feynman rules clear? Okay. All right, let me grab another, let me just grab a quick drink. Is it possible to get something without Michael Jackson on it? Here, I'll just get some water. All right. Okay, now, already if you just flat out do these computations, they're not that nice. They're much worse than scattering amplitudes, okay? So for instance, if we're doing this calculation just for a scalar theory with scattering amplitude, we just write down 1 over s, and we'd call it a day, okay? But what is the analog of this for? What is the analog of this for the for our computation? It's this integral d eta prime e to the I k1 plus k2 eta e to the I k3 plus k4 eta prime, and then we have these 1 over k intermediate for this guy, and then we have 3 terms: theta of eta minus eta prime e to the I k eta prime minus eta plus the other way around minus e to the I k eta k intermediate e to the I k intermediate eta prime, right? This is okay. So it's a sum of 3 terms. And I won't write them all out for you. It's not that hard to do the integral. It's a sum of 3 terms. Each term has this pole 1 over k intermediate, right? But they actually cancel. There's a simplification when you add all 3 terms up. And so let me just leave it as an exercise for you to do it in the sort of dumbest, most direct way. And let me just write down what the final answer turns out to be. Okay, so the final answer turns out to be, so this is naively 3 terms, but the 3 terms actually add up to something really simple. 1 over k1 plus k2 plus k intermediate, 1 over k3 plus k4 plus k intermediate, 1 over k1 plus k2 plus k3 plus k4. Okay, so this is our first interesting calculation involving a propagator. Okay? So it's already cool that the 3 terms collapse and they become a little bit simpler. Okay? Now, already with this expression, let's verify that it does the right thing. So now there is that pole as expected when the sum of all the k's, right? So what happens when that sum goes to 0? Okay, this is supposed to give us the S matrix. This is supposed to give us the scattering amplitude. But how does it do that? Well, when k1 plus k2 plus k3 plus k4 equals 0, on this pole, the residue is just these terms. It's 1 over k1 plus k2 plus k intermediate. And then it's 1 over, but k3 plus k4 is negative k1 plus k2 plus k intermediate. And so what we get is 1 over k intermediate squared minus k1 plus k2 squared, otherwise known as k1 plus k2 is the magnitude of the energy of the intermediate line. So this is otherwise known as 1 over s, which is the scattering amplitude. Okay? So that's pretty cool. The scattering amplitude is not really, we write it as 1 over s. In terms of Mandelstam's, it's a single pole, but it's fundamentally a double pole, right? It has 2 poles with the 2 different energy, positive and negative energy. That's related to the existence of antiparticles and all that good stuff, okay? So the cosmological object does not see it as a single thing. It sees it split up into 2 things, okay? But indeed, away from the pole, it doesn't look like a propagator. On the pole, these terms combine and they turn into propagators. Okay. But now I think you don't need to be convinced as we go to like 5 points, higher points. Every propagator has 3 terms. So this is complicated. Something that for an amplitude, you just write down 1 over S12, S123, 3, and so on, is, for example, at 5 points. Let's say I do the analogous calculation. I put some 3, 4, 5 here. This is now 9 terms. Okay? If you just do it from just flat out doing the integration, because each one of these propagators has 3 factors in it. Okay? So if you write them all out, it has 9 terms. So in general, even one diagram has an exponentially large number of terms. It scales like 3 to the power of the number of internal lines. Okay? And yet, when you actually do the calculations, they collapse. They're much simpler than you expect. Blah, 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 blah. All of that good stuff. Okay, now, so this is one representation of the amplitude as a time integral, okay? Of the wave function. This is the usual sort of Feynman path integral prescription. So, so let me abstract away what the rules are so that we can say it a little more nicely. So you see, whenever we have these diagrams, there's no real point in keeping track of all the lines going out to infinity, right? They're all just going to give us factors e to the I, k eta. And no matter how many lines we have, all that matters is the sort of composite total energy that they all have. Okay? So given any graph, we're going to prune it. And so, for instance, instead of having this graph, we're going to draw instead just this one. Instead of having this graph, we'll just draw this one. Okay, instead of having this graph, we'll just draw this one, and so on. Okay? So we eliminate all the reference to the lines going out to infinity.
This is only for qubit or
No, for anything.
but you draw the
Yeah.
same diagram if there are more lines.
Yeah, exactly. Okay? And because all that is giving you e to the I k1, k2, k3. So all that matters is the sum of all those energies. Okay? So what we do with every vertex variable, we associate some variables that we call x. And they represent just the sum of all the energies that end on that vertex. And all the intermediate lines we just call y. Okay? So now everything is reduced to some graph. You draw an arbitrarily complicated graph, any graph you like. But associated with that graph is a certain function that we get from doing this integral. So given a graph G, so for a given graph G, we're going to have a function f that depends on G, an x of the vertices and y of the edges, which is just the integral from minus infinity to 0 for the product of over all the vertices, d eta for the vertex. Each one has an e to the I x for each vertex. And then we have these propagators that depend on the y's for the edges and eta for some vertex eta edge of v1 and v2 associated with the edge, where this function is exactly what I wrote down. We can write it in terms of where g is 1 over y times this theta of eta minus eta prime e to the I, now x eta prime minus eta plus the other way around minus e to the I. Y. I apologize. E to the I y eta e to the I y eta prime. Okay, and actually it's more convenient to put a 2 here. Okay. But, all right. So that's the object of interest. You give me a graph. The graph has variables associated with the edges and the vertices, and that's the official Feynman diagram calculation of the graph. Okay? So let me see if I have one in my bag here. I don't remember the forms off the top of my head, but maybe I have one in here. Yes. Do any of you guys have a laptop open? Yeah, this is, I don't have. I guess it doesn't matter. Oh, here it is. Here it is. Okay, I'll just give. Yeah. So we have just to give 2 examples. So for example, just one thing is just x, and that's just 1 over x. There's nothing to do. Two things, two-site graph is x1 and x2 and y. So this is 1 over x1 plus y, 1 over x2 plus y, 1 over x1 plus x2. That's just what we talked about. And this three-site graph, that was the sum of 9 terms, is x1 plus x2 plus 2, sorry, is x1 plus y1 plus 2x2 plus y2 plus x3 over x1 plus x2 plus x3, x1 plus x2 plus y2, x2 plus x3 plus y1, x1 plus y1, x3 plus y2, and that's it. 1, 2, 3, 4, 5, 6. Whoops. Oh, sorry. And one more. x2 plus y1 plus y2. Okay. Oh, yeah. Okay. So, all right. So that's what you just get. And as I said, this was 3 terms that collapsed to 1. This was 9 terms that collapsed to this nice simple thing. Okay. So there's already lots of spurious pole cancellation, lots of this stuff, and this is what you get. All right. Now, so what do you do if you see this pattern, and you've heard any of the lectures that we talked about today? Well,
Sorry, are the poles got cancelled always something like 1 over y? Or?
sorry. Yes, and more generally other things as well. But just say this is a very good point. There's a very good reason the 1 over y's have to cancel, and the reason is that the pole as y goes to 0 is clearly not there in the actual propagator, right? So in the actual propagators, y goes 0 cancels. So this representation is chock full of spurious poles that must cancel. We know, but more generally, there are more things that cancel. It's not just these guys that cancel. Okay. But let me tell you what it is that you do with these. These are functions, right? But they're functions. They have poles. They have very interesting poles. There's cancellation. So what should you do? You should wonder if these might be telling you there might be some geometry associated with it. And again, always in this story, we don't sit around thinking about the geometry and find one. It's the forms that are telling us to be looking for them. And so what do? You have to stare at these things and think, what could this be? So already take the simplest example, right? What could this sucker be? If it's a geometry, just from what I told you earlier today, let's, hopefully none of you have read the paper with Paolo. I think hardly anyone has read it. So what could this geometry possibly be? If it was going to be a geometry, what geometry would you guess it is? There's no numerator. 3 poles. What do you think it is? Triangle. Excellent. You are the first private discoverer of a cosmological polytope, okay? Your own personal cosmological polytope. Yes, absolutely. It is a triangle. And so what should you put upstairs? So what are the variables? There are 3 variables in this problem, x1, x2, and x3. So what's the space that it lives in? It's the projective space of x1, x2, x3, okay? So if I put this x1, x2, x3 into a big vector, it would just be, I don't know, call them E for energies. It would be E, dE, dE, and then 3 poles in E. And that's the canonical form for a triangle. Okay? So that one was pretty easy, maybe lucky, right? But now that we know what we're looking for, let's go to this case. Now this thing is much more juicy, right? It has, so what space should it live in? What's the dimensionality of the space? x1, x2, x3, y1, y2. So it's 5-dimensional vectors, so it's P4. This is already a 4-dimensional polytope. If it's anything, right, it has to live in 4 dimensions. How many poles does it have? 1, 2, 3, 4, 5, 6 poles. So if it was a simplex in 4 dimensions, it would have 5 poles. So this is something slightly more interesting than a simplex, if it's anything. But before getting too excited, what should we do? What should we do to like see if this even has a chance? Maybe I didn't emphasize this enough before because I started with the story as if you knew there was a geometry ahead of time. But if you don't know there's a geometry ahead of time, you take any expression you have and then you take residues. You take residues and you keep going to see if by the time you're done you get 1 or minus 1 all the time. Right? And if you do, then at least you find that you have an object that has logarithmic singularities with residues 1 and minus 1. And if you have that, then you can hope there's a geometry, and so on. Okay? So in this case, as you take residues, you just shove it on Mathematica, you take residues, and yep, every way of taking it down, every way gives you 1 or minus 1. Okay? So now you start getting more excited. Maybe there is a geometry that goes along with it. But how can you guess what the geometry is? You still just have this function or this form. Well, here's the other part of the strategy, is you know something about what the face structure of this sucker has got to be, right? For example, you know it has to have 6 faces, because there are 6 poles. Okay? So it's a 4-dimensional object. It has 6 codimension 1 faces. Now you know something about the number of lower faces. How do you know that? If it were to exist, is you have to take, you go to one residue, you take another residue, okay? So you put another pole to 0. Some of them will be killed by the numerator, so they don't count as 1 lower dimensional faces. Some of them do. Okay? So you just do that on Mathematica. You just keep playing. So how many codimension 1 residues are there? How many codimension 2? How many codimension 3? How many codimension 4? By the time you're done, okay? So now you get a list of numbers. I don't remember what they are exactly in this problem. But now you get a list, this many faces, 6 faces, so many of the next dimension, so many of the next dimension, so many vertices, okay? So here's the next check that you can do. If it's a polytope, if it's a geometry, if you take the alternating sum, the Euler sum of v minus e plus f dot dot dot, you should get 0 or 2, okay? So you do that. And you get something that counts as being a polytope. Okay, so now you're getting more convinced that there's a geometric shape that goes along with it. And then literally what happens is that you say you have a polytope, it lives in 4 dimensions, it has this many faces, this many vertices, this many edges, and is there a 4-dimensional polytope? So you Wikipedia around a little and you don't find anything. And then you email your friend Alex Posnikov and you say, hey Alex, do you know any polytopes that have this many vertices, this many faces, this many things? And Alex emails you back 15 minutes later, well, yes, Nima, it's a double square pyramid, okay? Okay, and that's, then you know you have something, right? So that's actually, so there is a geometry that goes along with it, and it's just what I said. It's like a square, and it has one point in the 3rd dimension and a separate point in the 4th dimension. Okay, so it's a double square pyramid that lives, yeah. Okay, so that's what the geometry is. All right, so I'm just, so this is just an illustration. Now we can go back and I can pretend that none of this ever happened, and I can tell you an invariant definition of these polytopes, and we can have an infinite amount of fun talking about what they are. But this is an illustration of how this kind of research works, right? You find objects you're interested in, you suspect they might be geometric. Why do you suspect they might be geometric? Because first, there is tremendous, in their definition, there's lots of cancellation, spurious poles go away, and you get something simple. Next, you take a peek at residues. That's a huge one. You take a peek at residues and see if they have logarithmic singularities at all. Okay? So that's very non-trivial that they should have logarithmic singularity, so the residues are just 1 and minus 1 by the time that you're done. So that one checks. And once that happens, you're almost cooking with gas, but then you have various checks. These combinatorial counts, how many vertices, faces, edges, and so on, are another very good check, whether the thing that you're talking about, the story this form is trying to tell you, if it's trying to tell you a geometric story, there's lots of consistency checks that it has to satisfy before you even know explicitly what the geometry is. Yes? Right.
So the P3 polytope on the boundary, is it just a trahedron?
Yes. Yes, that's right.
All boundaries is just a trahedron?
No, one of them is a...
The numerator puts 0 on one of the...
Yes, all the boundaries are tetrahedral. Yes, that's right. That's right. That's right. That's right. Yeah, I mean, the polytope really looks like what I said. It looks like a square, and it looks like this, and then another point like that, but in a fourth dimension. Okay? Okay?
Why have
Yeah.
6 faces?
Huh?
You said you should have 6 faces though.
1, 2, 3, 4, 5, 6.
Isn't it the
Oh, it's in 4 dimensions.
No, this thing is self-dual. Yes, this is in 4 dimensions. Yes, that's right. Yeah. Yeah.
Sorry, it looks like 8 faces.
Yeah. No, but that's
No, but that's not what the convex hull actually looks like. Yeah. Sorry. Yeah. I mean, yes. Yeah. It's not. Yeah. So, yeah. In fact, we'll do another example in a moment. Yes.
Sorry. What if you work with one loop and you look at all the integrands and you want to...
Let me just talk about one loop, and I'll talk about one loop right now. So in fact, this is the next simplest object. Okay, this just depends on x1, x2, and so there's let's say y1, y2. And this thing just looks like 1 over x1 plus x2. So that's the thing that always has to be there. Then this is slightly more interesting, like we have x1 plus y1 plus y2, x2 plus y1 plus y2. X1 plus x2 plus 2y1, there's that funny 2y1, and x1 plus x2 plus 2y2. So this thing has 1, 2, 3, 4, 5. Yes, that's correct. 5. Yes. Okay. This thing has 5 poles, and it has a numerator, which is, I believe, just x1 plus x2 plus y1 plus y2. All right? Okay, now this is something else. Now what dimensionality does this thing live in? It lives in, there are 4 variables, so it lives in P3. Well, that says 3-dimensional. We should be able to visualize it. That's good. And what should it look like? It has 5 poles. It has a numerator. So there's not too many shapes that have 5 faces. So it actually looks like this guy. Okay. Something with, no, the thing itself, directly, yeah. Okay. It has 5 faces. Okay. Up, down, the 3 around. So those are the 5 faces. And I won't bother putting in what all the vertices correspond to, because we're going to understand all this from a deeper point of view momentarily. Okay? But I just want to give you, again, just give you an idea that this is a canonical form associated with a shape that looks like that. Okay? Huh? Yes, it's a dual of the cyclic polytope. Yes, it's a dual cyclic polytope. Yeah. Sorry, I thought you were saying, is this the dual? No, that's right. That's right. Okay, so, all right, so I hope I've whetted your appetite now for thinking about these objects. Let me just tell you one more thing, which is a different way of calculating it. Okay? There's a beautiful different way of calculating these objects. And in fact, you should expect there's a different way of calculating it, because after all, if this was flat space, nothing that I'm doing really cares about the things being a flat space or not. If it was flat space, this would literally be the vacuum wave function. And you know there's another way of calculating the vacuum wave function instead of the Feynman path integral. What is a way of calculating the vacuum wave function without the Feynman path integral? It's called solving the Schrodinger equation, right? Before you know about the Feynman path integral, you learn about solving the Schrodinger equation. So there's that way of doing the calculation, okay? And that way of doing a calculation gives you a totally different expansion that looks nothing like what I get from the time integral representation. In fact, it looks like old-fashioned perturbation theory, right? But we don't have to, I don't have to remind you about old-fashioned perturbation theory or anything like that. We're actually going to derive it in a very pretty way from the picture that we started with already. So let's go back to our formula. This function, which is now the integral over the product of the vertices dA to v. And remember, there's an e to the I x v a to v, and then there's the propagators g of y of eta e of a to v and a to v prime that are associated with that edge. All right?
When you say old-fashioned perturbation theory, you really mean
Old-fashioned perturbation theory. Huh?
with z-graphs?
With the z-graphs, exactly. That you could do with z-graphs, but what I'm about to tell you is the fast way of doing the z-graphs. Okay? I don't know. I mean, this was probably known to the people in the 1930s, but I don't know where to find that. So we'll just do it ourselves. Okay. So what we're going to do is insert in front here, let me define an operator, delta, to be minus I times the sum of all the dd etas for all the etas in the graph, however many there are. So just the sum over all the vertices, dd eta v. So what is this delta? This is overall time translation for everybody. Okay? And so what I'm going to do, so let me define this delta. What I'm going to do is shove a delta in front of that e to the I x a to v. So I'm going to look at the integral product over v dA to v. This delta only acting on e to the I x v a to v. This part, leaving the propagator part alone. Okay? So first of all, what do I get when I act with delta on all of these things? This is just pulling out the sum of all the x's. The sum of all x's times f. Okay, so this is just equal to the sum of all the x's times the original f on the one hand. On the other hand, let me use integration by parts to move the delta off of this guy and onto g. All right? So what happens? So on the one hand, this is equal to this. On the other hand, I'm going to use integration by parts. And I'm going to write this as the product of a to v, now back e to the I xv a to v. And I have this delta acting on these product of these propagators. The product over all the edges. This is the product over the edges. Delta acting on this g of y and eta prime. Okay? Now, one comment. I have this plus the boundary terms, right, from the integration by parts, because I'm cutting it off at eta equals 0. But here comes a nice first beautiful piece of, the first beautiful thing that happens. What are these boundary terms? The boundary terms just involve evaluating this propagator when some of the etas go to 0. But that's 0, precisely because these are the propagators for the wave function. So that's really cool. The boundary pieces disappear, precisely because this bulk Green's function, this bulk propagator disappears as you head towards the boundary. Okay? So the boundary terms are gone, and all I'm left with is this. But this operator, delta, acting on these propagators, has a beautiful interpretation. Let's see what delta does when it acts on one of these propagators. Okay? So let me do it here. So let's say I have delta. So let's say I have delta that acts on one factor of g, of y, and some particular a to 1 and a to 2, or a to v and a to v prime. Now, you see, you might think this g is complicated. It has a piece that with the theta functions and all of that stuff. But the piece with the theta functions only depends on eta minus eta prime. So that piece is annihilated by this uniform translation. Okay? So the only thing this does for any given edge, the piece with the theta functions is annihilated, just hits the piece with the e to the i's, and that just kills the 1 over y, right? So this just gives me e to the I, y for the edge, eta, e to the I, y for the edge, eta v prime. Beautiful, simple thing. Okay? So what does delta do as you apply it to the product of all the propagators? It's a linear operator, so we hit one of them at a time. Okay? But every propagator that it hits, so let's say I do this example where I had this guy. Let's say I look at that. Okay? And I'm taking delta multiplied by the product of all these things. Okay? Well, it's equal to delta on this times the rest plus delta on that plus delta on that. But what is delta on this? Delta on this just has the effect of removing that line. Okay? So I used to have some x here, some x1, x2, x3, x4, and there used to be a y, y prime, y double prime, let's say. Okay? But when delta hits this line, I get rid of all the theta function stuff, so that part is just gone. But I get this extra factor, e to the y energy, eta, e to the y energy, eta prime. As far as this integral goes, that's just as if I remove that, but I added y here, and I added y to the things that it touched. Okay? So the effect of delta is to go through the graph and snip one line at a time. Okay? And all the lines that it snips, you give the energy to the energy associated with the y to the vertices that it touched. Okay? And so that gives us a beautiful recursive formula for calculating. It's a little bit like BCFW. Beautiful recursive formula for calculating f, because the sum of all the energies on f is equal to this operation with delta, and therefore this is the formula, right? So let's do it in an example before writing down the general formula. So for instance, how do we calculate this guy? So this is x1, x2, and y. But we learned that f is equal to, we first write down 1 over x1 plus x2. OK? And then we just snip. So this is equal to this times that, where this is x1 plus y, x2 plus y. So therefore, this is equal to 1 over x1 plus x2, 1 over x1 plus y, 1 over x2 plus y. OK? No 3 terms, just 1 term. And similarly, we can calculate this guy, x1, x2, x3, y1, y2. Now this is just equal to 1 over x1 plus x2 plus x3 times. Now I snip this one, and I get 1 over x1 plus y, 1 over Now, this is the formula that we just computed a moment ago. So this is x2 plus y1 plus x3 times 1 over x2 plus y1 plus y2, 1 over x3 plus y2. That's one term. And then I have the other term where I snip the other one. So that's a sum of 2 terms. Okay? Not 9 terms. Okay? So this is a different representation of the wave function. All right? Yes?
So, yeah, well, that one was a little bit more complicated geometry. I cannot kind of visualize it. But just for the do of the
Yeah, so let's do this one. That's right.
The 2-term triangulation
Yes.
correspond to that.
Yes, yes.
And what about the 3-term triangulation?
There's no, that does not correspond to anything. It doesn't have any physics interpretation. Okay? But I will talk in a moment about what the different analogies are. Okay, so there's a 2-term formula here, and in fact, it's possible to write down the answer. So there's a recursive formula, obvious recursive formula that looks just like BCFW. You write 1 over the sum of all the energies, and then you go through the graph snipping one propagator at a time, and then you get the product of 2 lower pieces. It looks exactly like roughly just like BCFW. But you can even write down a formula ahead of time. Okay? You don't have to do it recursively. The rule is, I'll just say it roughly. It'll be sort of obvious why it works. You take the graph. You first put a big circle around it for the whole thing. Okay, so let me describe how the rule works in this example. And this just implements the recursion. Okay, so you put a big circle around the whole thing. So let's say you do this example. First, put a big circle around the whole thing. And you write down 1 over x1 plus x2 plus x3. And then you just go through and you divide it into subgraphs. So I take this one that are separated by an edge. Okay? So I decide I'm gonna split it in 2. So I'm gonna take these guys and then I circle the other ones. And then inside here I still decide. So I can circle that one and that one, for example. Okay? And then for everything that is circled, you write down, so this is y1, y2. You write down 1 over the sum of all the energies of the circled vertices plus the sum of all the energies of the edges that end on the circles from the outside. Okay? And then, so you then sum over all ways of doing this. Okay, so all ways of covering the graph with subgraphs that are connected by an edge as you go along. You see, this is just recursively putting in exactly what we did. We did the whole thing, and then one piece is, so snipping this is like separating that. And then inside here, snipping that is like separating that, and so on. Okay? So from this term, you would write down 1 over x1 plus x2 plus x3. And then from this guy, you'd write down 1 over x1 plus y1 by the rule that something that ends on it from the outside. From this one, you would write down 1 over x2 plus x3 plus y1. And then from the interior of both of them, you'd write down 1 over x2 plus y2 and 1 over x3 plus y2. And so this is one of the terms. Okay? And then there's another term where you break the graph up into connected subgraphs, connected by an edge in the other way. Okay? So this is a second representation of this wave function. The first representation in terms of the time integral, that gives you sum of a whole bunch of terms with spurious poles that cancel. This second representation is a sum of a bunch of terms, but there are no spurious poles. Okay? All the terms, all the poles that we have here are poles that end up in the answer. Okay? So if you know anything about n equals 4, this reminds you a lot of the difference between BCFW triangulations and local triangulations. So local formulas have these nice features. They only have physical poles. Anyway, so now something amusing though, if you take each one of these pieces individually, let me not get it. That's a little too much detail. For the moment, you just see there are two different representations. Notice one representation is explicitly bulk. It involves time integrals. This representation is explicitly boundary. I make no reference at all to the bulk. I'm just doing this manipulation directly on the graphs. You'll notice that we just have these sums of energies in the denominator, and that's what reminds you of old-fashioned perturbation theory. Okay, so that's exactly what we get exactly what you get when you do the calculations in old-fashioned perturbation theory. Okay. So now I'm going to tell you what the object is. Okay, so now I'm going to tell you what. Yes, it's actually a natural place to stop because you have to pee. So should we come back in around five minutes?